How do you get a feel? Your control system engineers now, you have to have a feeling for the time that things take. So how could you tell?
Time constant.
Time constant. So what's the time constant for this system? It's 1 over b. So after, I don't want to have it intersect with this one line, because the one line is just an input, but after, I'll have it come up here. So here's t equals tau equals 1 over b seconds. Then the output is 63% of the way to the final value. And so if b is really big, then tau is really small, which means it responds very quickly. If b is really small, then tau is big, which means it's slow. Any questions about that? Another kind of input, though, is an impulse. And an impulse is interesting. So I call it the Dirac delta function of t. It's basically an infinitely high pulse at time 0, but it has the property that if you integrate this dt, you get what? Integral of Dirac delta of t equals 1. That's the way it's defined from as long as you start before it, 0 to any time. It's 1. So that's just the definition of it. And they talk about it in the book. But so if that's the input, then what's the final value of y for this system? You're doing the same steps, but instead of that as an input, you give it an impulse. How do I get the final value of y? What changes in this thing? So that goes away, right? Because it's a 1. And so what's the final value of y then? 0, okay? According to this, for an impulse input, the final value is 0. And not only that, y would be y itself. For that case, what's y best? For any s, what's y best? For the input of 1, it's just a over s plus b. So then you can invert that easily. So what's y of t? A times e to the what? Minus bt. Okay, so what's y at time 0? A. So what it says is that even though the initial conditions are assumed to be 0, when you kick it with a hammer, an impulse, it gives you an initial condition. It's like giving it an initial condition, and you get so this could be A, I don't know what value it is, but say it's there, and it's going to exponentially go to 0. So this is with an impulse input, it goes to 0 exponentially. With a constant input, it goes to exponentially to whatever that steady state value is. So those are known as test signals, and we'll be talking more about that tomorrow on Friday, different test signals. But an impulse, a step, those are 2 of them. And then there's 3 other good test signals. But today I just want to look at step response, and mainly for this system. So this is a second order system, and if I give it a 1 over s for this system, depending on this characteristic equation, it's going to go to a final value. Guess what the final value is for this? Give it this input. What's the final value going to be? Just looking at that should be able to tell me. Well, it's going to be like before. The 2 s's we're going to cancel out. You do this, and it's s times whatever y is. Except now in the denominator you have the second order thing. these two S's cancel out, so what do? What do you get? Final value. A over C, right? So that's the final value of y. Steady state value of y in that case is A over C. And then how does it get there? How does it respond? It depends totally on B and C. Not on A. A just determines how high it goes. It depends on these two coefficients. And what's your guess? Should I put in, does it go like this? Does it go like this? What does it do? Yes, sir.
You can get both depending on how you value B and C.
You can get either one of those. That's correct. So that's really the whole point of, well, not the whole point of chapter 5, but one of the things about chapter 5 is how you predict the response given certain value of B and C. So in order to do that, we'll go back and think about this system in more detail. And also, the solution is kind of ugly, so I'm going to write down the solution, and you're welcome to use that in the book. You have these these Laplace transform pairs. So let's say that we're interested in the response of a system like this to a stepped input. And you look up in the book and you see, oh, well, from the book. So from a table in the book,